Yeah.
Okay, welcome to lecture, I believe this is 29. Guys, things are getting serious. Internet, this is the second most important day of your life. No, third most important day of your life, pre-FTC day. Wednesday will be FTC day. It is unmissable. It is the greatest thing ever. There will be party hats. There will be noisemakers. There will be any food that you guys bring. So, I don't know, one year someone made brownies and they decorated them with Riemann sums, with like it was like RM rectangles. It was pretty amazing. So it's gonna be awesome. Yes.
Wasn't last lecture 29?
Maybe this might be lecture 30. It's hard to say. What?
What does FTC even stand for?
Doesn't matter if you don't know. That's even better. Also, I think Ostrander's gonna be observing me, so it's gonna be great. All right. So this will be my annual evaluation. So if I get fired, it will be your fault. So, good. Last class was pretty amazing. Last class we talked about Riemann sums, is that correct? Can you put those under the periodic calculator? So today, and at the very end of class, we talked about Cinderella. And by the way, I went back and researched it by Googling bippity boppity boo. And just for the record, the mice turn into horses. There is also a horse who turns into the carriage driver. That's so. That's the thing, though. And the dog turns into the coach man who opens the door, like the door opener. Yeah, so that's just get that straight. Okay. So we talked about integration. Gerhard, we talked about integration. There are various properties of integration, which I want to talk about now. And each of these properties is like deep and can be understood on multiple levels. So I'm going to go kind of fast, but for each of these, well, let's give an example. Here is an example. Here is a fact. Fact. The integral from a to b of a constant function is what? Alice. Say it again.
Like c times the
Okay, actually, yeah, but that's true, but you can actually just give me the answer.
b minus a.
Yeah, this is going to be c times b minus a. How did she do that? How did she just know? Yes? If you draw a picture, it is really obvious. Can I have a blue marker? If you draw a picture, it's really obvious, yeah. And in fact, probably the best way to understand these various properties is to draw yourselves little pictures of them. So here is A and here is B, and what is this function C? Well, it's just a constant function which has value C like everywhere. So it looks like this, and if we interpret the integral as being the area under the curve, then this is just a rectangle like this. Good so far? Yes?
Would it C negative though?
I'm going to scoot this over. Well, if C is negative, then the picture is going to look different, but I think it's still going to be the same answer, right?
But it's not. Is it negative or positive?
Negative. We hear last class?
Oh, yeah.
Yeah. But perhaps, well, actually, what I'm about to do now might address your concern, which is I would like everyone to understand this on the level of picture, because I think it's the most intuitive way, but we can also do it using the technical definition of an integral. So, Shivani, the technical definition of an integral is the limit of a Riemann sum. So, this integral is really the limit, as n goes to infinity, of the sum from I equals 1 to n of f of x sub I star delta x sub I. So recall that that is actually what we do when we actually do an integral instead. We take a function, a continuous function, a closed interval. We take that interval, we partition it up into subintervals in some kind of way so that the partition is a good one. We choose a sample point from each subinterval. We evaluate that function at that sample point. We multiply it by the width of the subinterval. We add them all up, and then we take the limit as n goes to infinity. Okay, how is that relevant to this problem? Should we be able to recover this answer from this formal definition of an integral? Yes, I think we can. And I think there's more understanding to be gained from actually doing this. So this is the sum from I equals 1 to n. Well, what is f of x sub I star in this particular case? Everybody. Yes, no matter how I partition the interval, and no matter what sample point I choose, when I plug that sample point into this particular function, since it's a constant function, the y value that comes out is always going to be c. Is everyone cool with that? Say yes. Good. How about delta x sub I? Well, let's assume for the moment that we are choosing equal width subintervals. Samin, if we are choosing equal width subintervals, then what is delta x in this case? Yeah, exactly. If we have n, assuming we have n subintervals, then Samin says, duh, delta x is just going to be the width of the interval, which is b minus a over n. So for delta x, I'm going to write b minus a over n. Okay? So this is kind of like a proof of this property. Okay, what can we do now? Fast, 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 fast. What can we do now, Buses? You're raising your hand? Calvin? Somebody?
Can't you like, I don't know, I would just start doing the limit at this point.
Sandeep?
The sum of all the c's from I equals 1 to n is n times c.
Yeah, in fact, we can just pull anything out of this summation, which is not, what can we pull out?
Wait, c.
Everything. We can pull out any constants. Is c a constant? Is b a constant? Is a constant? Is n a constant? Also, yeah, right? Yeah, so that's exactly what I'm going to do. I think that's the easiest way to do it. So we take the limit, but what you said is also correct. The limit as n approaches infinity of, I just pull out everything which is a constant with respect to the summation side. The summation is from I equals 1 to n, so I is truly the variable, so this is really just like a 1. And Sandeep, what is the sum from I equals 1 to n of 1? That's like 1 plus 1 plus 1, n times, that's just n. So that becomes n, and this is c times b minus a over n times n. The n's cancel. Is everyone cool? Say yes. The n's cancel, and the limit as n goes to infinity of just constant is just c times b minus a. Okay, so yeah, that is like a rigorous proof of the fact that this is true regardless of whether c is positive or negative, and maybe that sheds some light on that. Okay, that is one sort of obvious property of integration. Here's another one that I think is kind of interesting. What is the integral from a to c of f of x d of x plus the integral from c to b of f of x? Think about that for a second. Magna, what should this be? These were also all in the book, but they were just like listed, like, here's the math. I want to understand it on a deep level, or I don't know, some levels. I don't even know what you mean by integral formula. But the integral, if I'm taking the integral from a to c of some function plus the integral from c to b, class.
A to C.
Yeah, that's right. Yeah, this would just be the integral from a to b. Why? Magna, why? Yeah, if you just draw it, it's just like duh. I agree. Yeah, you just kind of start integrating and then you just keep going, right? What does this say? This says, if we make a little picture of this, here's A, here's C, here's B, some kind of a function or whatever. And if I take the integral from A to C, well, I can represent that graphically with this like blue area. And then if I take the integral from C to B, well, I can represent that graphically with this red area. And if I add those two numbers up, then I should get the integral from A to B, right? It's like so obvious. Okay, here's the thing. I would also like to understand this on a deeper level. Why is this true using the formal definition of the integral as the limit of a Riemann sum? Well, this would be the limit, as n goes to infinity, of, well, what is this? This is going to be the sum I equals 1 to n of f of x sub I star, and then what is delta x in this case, assuming we have n subintervals? No, the first one, I'm doing just this one. This would be c minus a over n, right? Yeah, this would be c minus a over n. That's the width of each subinterval over here. And then plus the limit as n goes to infinity. Now I'm doing this second integral. This would be the sum from I equals 1 to n of f of x sub I star. And now delta x for the second integral should be
b minus c over n.
yeah, b minus c over n. Yup. Cool. Okay, what can I do with this mess?
Pull out constant.
Kind of only like one thing that must be done first, at least I have to say it.
Combine the limit.
Combine the limits. Yeah, L says that is like a thing going all the way back to, the first 2 weeks of this class. The limit of a sum is the sum of the limits, right? So if I'm taking the limit of one thing plus the limit of another thing, am I allowed to combine that into one big limit?
Yeah.
Yes, I am, provided the limits exist. So I'm going to combine this into one big limit. So I have one big limit, and well, inside this limit, I guess I'll just rewrite it, because like whatever. So I have a little bit of this, and then I have c minus a over n plus the sum from I equals 1 to n of f of x sub I star b minus c over n. So, okay, now that I've combined the limits, now what?
Pull out constants, which is like c minus a and b minus c, I think.
Okay, he wants to pull, actually, could I just do something even simpler first, maybe? Well, I guess it doesn't really matter the order in which you do it. But, can I just combine the sigmas?
Sure.
Yeah, I can, right? Because look, oh man, Monday. Yeah, I can just combine the sigmas. Because look, I'm just taking the sum from I equals 1 to n. So here I'm adding, maybe it's because I just drank a bunch of coffee last period, so now you guys seem slow. Wake up!
We have some coffee as well.
You can have some coffee, yeah. Good. So Mateo, look, I'm adding up n things here, right? Here I'm adding up n things. Let me relax a little. Here I'm adding up n things. And here I'm also adding up n things. So does the order in which I add up the n things matter?
No.
No. So could I just n times add up 2 things?
Yes.
Of course I can. And so, basically, after, in my first step, applying a property of limits, now I'm going to apply a property of sigmas, which says that I can just, like, put them all together into one big sigma. You guys okay with that? Okay, so this is f of x sub I star c minus a over n plus f of x sub I star b minus c over n in one big sigma. And then you take the limit as n equals 3. Okay, now what?
Factor out an f of x I star.
Yes, factor out an f of x sub I star, he says, and then what's left?
A constant that you can pull out.
B minus A.
Yeah, this is going to be c minus a plus b minus c over n, some limit. And what is that?
Just b minus a over n.
That is just b minus a over n. It's like magic. Arun, are their heads in the way?
I think it's good in a little bit, but not yet.
What is that limit by definition? It's that integral on the right. I don't know, are you impressed? I think this is like cool. I think it's really cool. Okay. Any one of these common sense things can be proved by really like treating the integral as a sum. An integral really is a sum, it's just infinite sum. What? This was all in the homework. I know, that's why we can go kind of fast. But did they do this like in the homework? No. This is like a proof. This is like a proof of the properties that you already had to use on the homework. Yeah, I know. So you should be comfortable with the things and why they're true on an intuitive level. We're talking, all right, let's just go faster. How about the integral from a to b of f of x plus g of x? What can I say about that integral? Sydney, if it was in the homework, what's the answer? Let's put this up into the integral f plus the integral of g. Why? It's not an answer. Why? Maybe this time it makes sense to just first do it with the Riemann sum definition. I don't know. So we're taking the limit as n goes to infinity of the sum from I equals 1 to n of, well, what's our function now? Our function is the f plus g function. So in each subinterval, we choose a sample point and we find the value of f and the value of g times, I'll just write delta x this time. Okay. What can I do with that?
Well, part of the sum is since you can do the opposite also.
Yeah, Calvin says just do basically just like do like the distributive property essentially, right? He says multiply through this delta x through both of these, and then instead of adding up n times two things, just add up n things and then add up n things, right? So again, what we're using now is a property, just a property of sigmas, which says that if you add up a bunch of things, the order in which you add them up doesn't matter. Everybody with me?
Yep.
Now what?
Split them into two limits.
Now again we apply a limit law, right? The limit of a sum is the sum of the limits. So this becomes the limit as n goes to infinity of the sum from I equals 1 to n f of x of I star x plus the limit as n goes to infinity sum from I equals 1 to n g of x of I star delta x. And now each of these, this is by definition the integral from a to b of f, and this is by definition the integral from a to b of g. Okay, the picture of this is, in my opinion, a little bit harder, right? So what does the picture of this look like? Well, okay, let me try to draw it. I guess it's something like this. So here's my integral. And let's take some function. Let's suppose that function looks kind of like that. So let's call this function f. And then let me make a new function g. And maybe g looks kind of like that. Okay, so that's like g. Alright, so let's try to make, let's try to make a picture. Can I get that green? So first we can take the integral from a to b of f. That's this red. So that's like what this integral represents, right? And then we take the integral from a to b of g. Well, that's now going to represent all of this stuff like under the green, right? You guys with me?
Yeah.
Okay. And now what I need to now draw is the f plus g function. Okay, that's kind of hard. What is the f plus g function? By definition, that's just the function whose sum is like the sum of the y. So I'm going to do some like fake graphical addition now. I guess it's like maybe like that-ish. Then it's going to kind of be like, maybe like, I don't know. This is hard to draw.
Just move the red stuff above.
Think that's about right?
Isn't it steep?
I
Yes,
think
it
it's a
should
little
be
more,
like
more steep, right?
Yeah.
Something like that, yeah?
Yeah.
Something like that. Okay, so that's decent. Okay, and then, so the f plus g function is all this. It's all of this area, so I'll just like, it's all this blue. Okay, so is it obvious that the green plus red equals blue?
Yeah.
I don't find it to be totally obvious, right?
Makes sense.
It makes sense. It's very plausible. It looks like it should be kind of right. But is it obvious? I don't think it's obvious. I find the actual, the proof via this one I find to be very, very clear. Here, could someone give an explanation that maybe actually makes it obvious? Everyone think about this for 20 seconds. Why should this be true? On an intuitive basis, maybe.
So the way we're calculating the area is basically by splitting it up into a bunch of tiny little rectangles, which is basically the height up to that point. And when we sum the graphs together, we're just summing the heights of the graph at any one point.
Yeah.
Basically, it's doing the same thing.
Yeah. You have to constantly be thinking about the rectangles when you're thinking about what integration actually means. What Buse I'll translate what Buse is saying. What Buse is saying is, look, he says we're basically just doing rectangles, right? So take an arbitrary subinterval. Take the ith subinterval. What do I do with the ith subinterval? I choose a sample point on the ith subinterval. And then what happens to that sample point? Well, I plug it into the f function. And I get a rectangle. and I get a rectangle of a particular height. The particular height of that rectangle is like determined by this like red thing or whatever, right? And then what do? That's what I do when I make this integral. When I make this integral, I plug that same sample point, that x sub I star sample point, into the g function, and I get a rectangle of this height, and it's gonna be it's gonna have area of like whatever this green thingy is, right? And then I plug that same sample point into the f plus g function. But what is the f plus g function by definition? The f plus g function is just the sum of the f function and the g function at that point. And so this rectangle has a height which is equal to the sum of the heights of those two rectangles. Because it doesn't look so good here, but it's okay.
Why can't you say it was a red symbol on
You're saying I should have put red on top of green for color purposes?
the Yes.
Yeah, I'm sorry. Made a bad stylistic choice. Nonetheless, do you guys see that by the definition of function addition, this blue rectangle must have height which is equal to the sum of the height of the red rectangle and the height of the green rectangle, right? That's just the definition of function addition. And so, since they have the same width, and the blue rectangle is, the area of the blue rectangle is the sum of the area of the red rectangle and the green rectangle for that subinterval. And since that's true for every subinterval, then that's true for the whole interval. Mateo, cool? That's like the intuitive understanding, which is really just a picture of actually what we did over here. Okay. I think these pictures are beautiful. I don't know what you guys think. Should we like skip around a little bit? I don't know. 1, 2 more, 3 more. How about this one, which says that the integral from a to b of a constant times a function? What is this?
Wait, did we just
Similar. That was a
Whoa.
rectangle. Here, what's the answer?
And then
just take out
c times.
Take out the constant.
and then do the
Yeah. Why? Why is that allowed?
like was constant.
Yeah. Let's just do. Okay.
Because the constant's constant.
So yeah. So we have basically what we have is the limit as n versus infinity from some equals 1 to n of the function, which is c times f of x sub I star delta x, and then basically like what do we do?
Pull out the c.
Just pull the c out of yeah, that's exactly what you said. Pull the c out of the sigma because that's allowed, right? And then pull the c out of the limit because that's allowed. And so yeah, so this is just like can be done in basically just like one line, right? It is also and this just is c times the integral from a to b. And of course this also has a picture associated with it. If I have some function on the interval from a to b, and maybe the function looks like this or whatever, then let's suppose like c is like 2 or something. So then this would be so that this would be the area under the curve. But then if I double this function, then what happens to the area?
It doubles.
It doubles, yeah. Why does the area double? Well, again, it's that same kind of Mateo.
Could you just make it like adding like another version of the function, kind of like question 3? Like if you're doing doubling, for instance, that's just f of x plus f of x.
Yeah, to the extent that multiplication is just like a sum of like another function, I guess, yeah. Yeah, I guess. But you still have to, well, yeah. If it really was just double, if it was really double, what if c was like 1.2 or something like that? I don't know.
Just like 0.2 times
Well, you're
plus
subtracting
0.2 times the
functions,
thing. Oh yeah, but then yeah.
I don't know, it is kind of, you can't sort of totally get rid of multiplication if you're going to have non-integers. But anyway, the situation is basically the same, right? If I go to the ith subinterval, the height of this rectangle and the height of this rectangle, the taller rectangle has to be precisely c times the height of the other rectangle in order for this whole thing to work, right? If this is the f function and this is the cf function, then the height of the rectangle, the height of the ith rectangle must be c times the height of the f rectangle. And so if each rectangle has twice the area, then the whole integral has twice the area. That works for any c. Okay. Yo.
So why do you if we use the same symbol for like integers and intervals?
Oh, it's not the same symbol. Don't forget, an interval is a number. An interval is a number. So in all of these things, we're computing, numbers. We have integrals and numbers.
Simple that
Okay, good, two more. What is the integral from a to a of some function? What is this?
F of X.
Robbie Fleischman, integral from a to a of an f?
It's like, oh, 0, 0. Oh, A to A, 0, yeah.
Yeah. Yeah, this is, I'm never drinking coffee again, you guys seem so slow. Yeah, the answer is definitely 0, why?
Because there's no will.
Yeah, because it's 0 because it's just like no, right? Because you're just going from A to A. Okay, that's one answer, maybe another answer. Pretty much, yup. Mateo says, just look man, the limit as n goes to infinity of the sum from I equals 1 to n of, Arun, can you raise it back forward?
Yeah.
Of f of x of I star, and then what is delta x in this case? Yeah, delta x is like a minus a over n. So delta x is 0, so for every single subinterval, delta x is just 0. So as this is just 0, then the product is 0, so I'm adding up a whole bunch of zeros, so this is just 0. Yeah, cool. Okay, another one. This is in the book. You may have found this slightly mysterious, or you may have found it to be obvious. Let's take the integral from 6 to 2 of some kind of a function. What's up with this weird business?
Backwards.
Backwards. Yeah, explain. Backwards. Explain.
It's like back and backwards, backwards. I don't know, it's just kind of like, it just is. It's like the same thing.
What?
Yeah.
dx to delta x. We realized class? Did people already move? Yeah. Oh, man. Here it is. What's going on?
Do you remember the metaphor that has to do with
Because remember the delta x in the sigma turned into dx. Everything became fairly small.
Wait, would that mean it have negative area?
Yeah, it'd be like 2 minus 6 over n.
Wait, do you guys not know? What? You kind of can, right? So math. So technically, what is this? Let's try to figure this out. This would be the limit as n goes to infinity of the sum from I equals 1 to n of f of x of I star times, but what's delta x now? Yeah, delta x is like 2 minus 6 over n. Yes, so that's right. If the function is positive, you can kind of think of this as integrating backwards. Right? Now our delta x's are in fact negative. Well, if delta x is negative, then how is each one of these rectangles going to contribute to the sum? If the function is positive, but the delta x is negative, then the product of the two will be negative, right? So I call these backwards rectangles. Also an unofficial term you should not write on the AP exam. But it's worth talking about, backwards rectangles. And if the function is positive and the delta x is negative, then they're backwards rectangles. They contribute negatively to the Riemann sum, right? So it stands to reason that this whole thing is going to be negative. Of course, what's one thing I could do is I could just write this as negative 4 over n, and then do what? What's up?
Pull out a negative.
Pull out a negative. Is that what you said? Yeah, pull out a negative. So if you pull out a negative, you end up with the limit as n goes to infinity I'll just pull can I pull the negative out of the limit also? So if I pull the negative out of the limit, I have negative limit as n goes to infinity of the sum from I equals 1 to n of f of x of I star, and now it's just 4 over n is my delta x. And so the final answer is that this is the opposite of the integral from 2 to 6. This was in the book, right? But they just, typical Larson bull crap, he just kind of like says, yo, here's the thing. Don't
I
ask
kind
me a
of
question.
like that.
You like that?
Yeah. Just like
Magnet program. All right, so this is So what is the integral from a to b of some function if b is less than a, or actually even if it's not? In fact, we just proved, except we did it with particular numbers just to make it easier, that this is just the opposite of the integral from b to a of some function. Agree? Say yes. Yo.
And what if you like my favorite?
It means exactly what it means.
So
It
like
means
it's
that.
negative.
First of all, we already have seen that integrals can be negative, right?
Right, but even when you have the.
Even like already, before, what I mean. One interpretation is in terms of position and velocity. Right? How much I want to say about this. But if I have a function with negative velocity, then a particular rectangle does have meaning. If this is a velocity versus time curve, if my velocity is negative, and I multiply by a positive delta x, I'm going to get a negative rectangle. The meaning of that would be that the change in position over that small time interval was negative, which is what the integral is meant to tell me. Okay, don't want to follow up on that any longer. What?
For like the other formula, what if it's like integral from 0 to 0 of 1 over x squared?
Okay, they're getting into like technical questions. I don't know. The function has to be continuous. All these things assume some kind of continuity. So, I don't know. Yeah, I don't know. Ignoring. Okay. There was also a homework. How did that go? Let's put these problems up on the board.
My favorite one.
So we'll do 1, 2. So everyone, take out this worksheet, grab a marker, and let's do it.
Like that. I feel like that's the one we should do. It's like the A to C and C to C. Yeah. I'm not crossing out. Oh wait, I was for that. I mean, they don't.
Up the board, up the board.
That's like how I think about it. Oh, me. I got one.
Wait, 1, 2. He did. What worksheet is this?
Oh, the
What am I doing?
Wait, what is what? Oh,
Guys are so slow. Come on, stand up. Oh no, you're not allowed to write.
wait, what is this a worksheet?
Put one on the board? Okay. Can you make it like really, really neat?
I call number 6. If anyone touches number 6. Bonnie, so I want to do 3. Damn it, City's the 6. No. No. Where are the markers? When you know. Are you going? Can we just write the answers?
I can't associate like you got.
Please put the original problem. Please draw a picture. Please put the answer, but definitely the original problem and a picture.